Welcome to this tutorial on gas-oil separation and compression. We'll follow the flow from the wellhead to the export pipeline, paying special attention to the instrumentation, the sensors that measure the process, the controllers that make the decisions, and the actuators that act on it. A production well doesn't deliver clean oil. It delivers a high-pressure, three-phase mixture of crude oil, natural gas, and salty produced water. The facility's job is to split these phases, stabilize the crude for storage, and compress the gas for export. Flow arrives through the wellhead choke valve, which drops the pressure and limits flow into the production manifold, and from there into the first main process, the high-pressure three-phase separator. The separator is a horizontal pressure vessel that uses gravity and residence time to split the phases by density. The well stream slams into an inlet diverter, which absorbs momentum and makes the first rough split between liquid and vapor. Liquids fall into the gravity settling section, where water, being denser, sinks to the bottom, while a distinct oil layer floats on top. Downstream, a weir plate holds back the water while oil spills over into the oil bucket. Gas travels along the top of the vessel and passes through a mist extractor, a mesh pad that strips out entrained liquid droplets before the gas leaves. 3 outlets, 3 phases: gas from the dome, oil from the bucket, water from the bottom. The physics is simple. Keeping it stable under changing well conditions is the control problem. Every separator runs 3 basic control loops. First, pressure. Transmitter PT101 measures vessel pressure and sends it, classically as a 4 to 20 mA signal, to pressure controller PIC101. The controller compares the process variable to its set point and runs a PID algorithm, proportional, integral, derivative, to compute an output that drives the pressure control valve on the gas outlet. Pressure rising, open the valve and release more gas. Falling, pinch it back. This is back pressure control. Second, the oil level. A level transmitter, a displacer or guided wave radar, feeds level controller LIC102, which throttles the oil dump valve. Third, the oil-water interface, measured by an interface-level transmitter and controlled with the water dump valve. Hold the interface too high, and water carries over into the oil. Too low, and oil escapes with the water. The actuators are pneumatic control valves. The controller's electrical signal goes to a positioner, which converts it into air pressure on a diaphragm, moving the valve stem against a spring. Every valve has a designed fail-safe state on loss of air or signal. The gas valve fails open to relieve pressure. The liquid dump valves fail closed to keep inventory in the vessel. Around the control layer sits an independent protection layer. Separate switches, high level, low level, high pressure, feed a safety instrumented system. A dedicated logic solver that doesn't ask the basic controller's opinion. On high pressure, it closes the inlet shutdown valve and trips the well. And if everything else fails, a mechanical relief valve lifts and sends the vessel contents to the flare. Control keeps you at set point. Safety keeps you alive. One separator isn't enough. Dropping a 90-bar well stream to atmospheric pressure in a single flash would boil off valuable light components and leave the crude unstable. So we separate in stages: high pressure, low pressure, then a stabilizer or stock tank, letting gas flash off gently at each step. Each stage's gas feeds a matching stage of compression, and the crude leaves stabilized, meeting its vapor pressure spec for storage. That flashed gas is at low pressure, and the export pipeline may need 100 bar or more. Enter the centrifugal compressor. Gas first passes a suction scrubber, a knockout drum whose only job is to catch liquid droplets because liquid slugs destroy compressor internals. Note its own level loop and high level trip. The compressor's impellers then accelerate the gas and convert that velocity into pressure. Compression heats the gas, so an after-cooler brings the temperature back down. Look at the instrumentation cluster around the machine: pressure and temperature transmitters on suction and discharge. a flow element in the suction line, measuring differential pressure, a speed probe on the shaft, and vibration and axial displacement probes on the bearings, wired to a machinery protection system that trips the unit in milliseconds if the rotor misbehaves. A performance controller regulates capacity, adjusting driver speed to hold suction pressure at set point. Now, the most important control problem in compression: surge. A centrifugal compressor can only develop so much head at a given flow. Map its behavior, head versus flow, one curve per speed, and there's a boundary on the left called the surge line. Cross it and flow through the machine actually reverses. Gas slams backward, then forward, oscillating several times per second, hammering the thrust bearings and overheating the gas. Seconds of surge can wreck a machine worth millions. The defense is the anti-surge controller. From the flow element's differential pressure, plus suction and discharge pressures and temperatures, it continuously computes the operating point and its distance to surge. Engineers draw a surge control line about 10% to the right as a safety margin. When the operating point reaches that line, the controller opens the anti-surge valve, a fast-stroke, fail-open-recycle valve, routing cooled discharge gas back to the suction scrubber, raising flow through the machine and pulling it away from surge. Watch it live. The export valve closes. Say, a pipeline trip. Forward flow collapses, and the operating point slides left toward the surge line. As it crosses the control line, the anti-surge controller responds with asymmetric PI action, fast to open, slow to close, plus an open-loop kick that snaps the valve open if the approach is too fast. The point rides the control line, the machine stays safely on recycle, and it never surges. And since the anti-surge and performance controllers interact, real installations decouple the two loops. Step back, and you can see the full control architecture. Level 0, the physical process, sensors and actuators in the field. Level 1, the controllers, the distributed control system, or programmable logic controllers, running the PID loops, plus the dedicated anti-surge controller, scanning many times per second. Level 2, supervision, the operator's HMI screens, the alarm system, and the historian. And beside it all, on its own hardware, the safety instrumented system, with 2 out of 3 voted sensors rated to a safety integrity level. Every one of these signals, the 4 to 20 milliamp loops, the field bus, the trip logic, is also an attack surface, which is why process control and cybersecurity now go hand in hand. Let's put the whole plant together and hit it with a realistic upset. A slug of liquid arrives from the flow line. Separator level spikes. The level controller drives the dump valve open. Pressure jumps. The pressure controller vents more gas to compression. The compressor's operating point shifts, and the anti-surge controller trims its margin. Layer by layer, loop by loop, the plant rides through the disturbance. No alarms, no trips, no flaring. That's the anatomy of gas-oil separation and compression. Gravity doing the separating, staged pressure letting the crude stabilize, machines doing the compressing, and a hierarchy of sensors, controllers, actuators, and safety systems, holding it all inside a safe operating envelope. Next time you see a P&ID, read it the way we did today. Find the transmitters, follow them to their controllers, and ask what each valve does when things go wrong. Thanks for watching.